Sadly, we're at the end of Chapter 5. The last topic in the gas unit deals with moving particles, moving gas particles. We're going to compare their rates of diffusion and effusion. Diffusion is a very general term, which just refers to the movement of fluids, so it could be either gas particles or liquid, from an area of high concentration to low concentration. So I could put 1 drop of food coloring in a container of water, and eventually the food coloring will become evenly distributed throughout the water. So we eventually reach a state of equilibrium where the particles are evenly distributed. Effusion is the same concept, gases moving from high concentration to low, but now we're going to specify that those gas particles are moving through a tiny opening. So if I pop a balloon in the front of the room, eventually, I don't know, let's say it was full of a smelly gas, we would eventually all smell the gas. Popping a big balloon might be more of an example of diffusion. The gas particles are eventually going to go from high concentration to low, and they'll become evenly mixed in the classroom. Effusion might be now I just make a little pinhole in the balloon, kind of like this picture where the gas particles are still moving from high concentration to low, but through a tiny opening. Now, this equation at the bottom is in your AP packet, and I haven't used it a whole lot lately. You can use this equation to compare velocities or speeds of different gas particles. Now, velocity would be measured usually in units of meters per second. So we are measuring how fast these particles are moving. Their speed or velocity is inversely proportional to their mass, which kind of makes sense. I mean, if I have some giant particle, it should move slower than some little baby particles. So if I had a balloon filled with helium and a balloon filled with xenon, and I popped a tiny little pinhole in each balloon, they might ask me which balloon will deflate faster. And then I would say, well, the helium balloon. The helium particles are smaller and they have less mass, so they'll move faster out of that tiny opening than heavier particles like xenon. If I wanted to calculate the exact amount of kinetic energy per particle, I could use this equation, and I'll show you that in the packet too. This 1/2 mv squared will calculate the kinetic energy per particle. Now that could be a molecule or an atom, depending on the identity of your gas. It's a little different than temperature. Temperature is another measure of kinetic energy. Temperature measures average kinetic energy. On average, how fast are the particles moving? Which we kind of looked at in that bell curve graph that you could get a reading on your thermometer, and that's the average amount of kinetic energy amongst a large sample of particles. There's always some molecules with more energy and some molecules with less. You can use this 1/2 mv squared to calculate the kinetic energy per particle. Now, often I've seen this more qualitative. So it might look like this. We have 3 identical flasks. So I'm assuming that means they are, the same size, same volume. They're at the same temperature. They're filled with 3 different gases: carbon monoxide, nitrogen, and hydrogen. They have different pressures. Ooh, that could be exciting. But again, same temperature. In which flask will molecules have the greatest average kinetic energy? Average kinetic energy, this is going to be a measure of temperature. If they're all at the same temperature, they have the same average kinetic energy. Awesome. In which flask will particles have the greatest average velocity? Now that's measuring in units of meters per second. Velocity depends on mass. So then I'm going to look at the masses of these different particles. Carbon monoxide, let's just say we kind of estimate Carbon about 12, oxygen about 16. So maybe this guy's like 28 grams per mole. Maybe this one's like, I don't know, 14 times 2, 28 grams per mole. Ooh, tricky. They're about the same. And the last one, oh, there we go. Hydrogen, let's say about 2. The one that should move the fastest, hydrogen. They have the smallest mass. So just kind of watch how they'll word it. Average kinetic energy refers to temperature. Average velocity is going to refer to that 1/2 mv squared, where now we're looking at the mass of the particles. The smaller the mass, the faster the particles move, and so then I can compare like rates of diffusion or effusion. The smaller the particle, the faster they should move. Here's a good example. Check out this experiment. We'll try to do this in class, and sometimes we get a good reading, and just qualitatively. We've got some kind of a long glass tube with 2 cotton balls. One of them is soaked in an ammonia solution. The other one is soaked in a hydrochloric acid solution. However, HCl and NH3 ammonia are typically gases, but they're dissolved in water as we use them in the lab as solutions. When the 2 gases react, they'll form a solid precipitate of ammonium chloride. So they want to know where the precipitate ring is most likely to be formed. So if I kind of compare the masses of these particles, and again, we can just estimate, maybe like chlorine, let's call it about 35. So chlorine and a hydrogen, let's say approximately like 36 grams per mole. And ammonia, NH3, let's call that about 17. Approximately 17 grams per mole. Okay, so I know the ammonia molecules are smaller, they're lighter. They should travel faster. I should expect a precipitate to form somewhere closer to C. So this would be like my precipitate. It's like a white solid. The ammonia molecules are going to travel faster, so they're going to meet up with the HCl molecules closer to that end of the tube. And then I'd see a white precipitate. So again, often these are just used qualitatively to compare rates of moving gas particles, rates of effusion or diffusion. And if we're talking about how fast particular particles would move, we do take their mass into consideration.